In this video I'm going to go over 3DMigoto's custom shader feature. Now I must say I'm actually a little bit surprised that this feature was raised as a concern at all. The automatic crosshair I could sort of understand was probably a misunderstanding of what the term automatic means in this context, but I would have thought that custom shader injection would be pretty self-explanatory. But regardless, I'll go through what we actually use this feature for, and if there are any specific concerns, perhaps those could be raised and I can address them more directly. Now, I do want to mention what this video is not going to be about. Well, taking a step back, firstly, as I mentioned in the previous video about the automatic crosshair, 3D Vision is an NVIDIA technology that will automatically convert video games into stereoscopic 3D. And the way that NVIDIA's technology does this is by patching shaders in games to inject stereo corrections. However, as I showed in the previous video, that the result of that looks like this, which is not very useful in any modern game. It only really works in very graphically simple games. It doesn't really work in any AAA or even indie game these days. So 3DMigoto does also patch shaders to complete that process. For instance, just in this scene, it would patch the water shader to inject a stereo correction to remove that nasty hole in the water. It would patch the reflection shader on the water to correct the depth of the reflections. There's actually a little bit more to it than that. It also needs to patch the output position of the objects in the reflection. We would patch the shadow shaders to correct the shadow position to make them line up with the ground. The clouds over there have a similar issue to the hole in the water, and there's a bunch of other similar issues throughout the game. The vast majority of all effects that we fix in a game are done by patching shaders, but that's not what this video is about. This video is specifically about the custom shaders that were queried. So there are a few different things that we use custom shaders for, but I mean, fundamentally a custom shader is adding a shader that's not already in the game. We're not patching shaders with this feature. So for example, the NVIDIA 3D Vision technology, when you're using it with a 3D television or a 3D projector, only supports some very limited output modes. It supports something called 3D TV Play, which is a sort of NVIDIA proprietary thing, which is essentially frame packing, but it's limited to 720p, and it supports HDMI checkerboard modes. It does not support side-by-side, over-under, or line interlaced modes. And so one of our custom shaders adds these features. So if I enable the custom shader in the configuration and press the F11 key in most games, in this game F11 is used for something else, so I've got it set to something else, then the first stage is it's actually reversed the stereo. So this is still doing regular 3D vision, but the stereo is reversed. This is useful for people with certain unusual setups where they're using the NVIDIA glasses with external television or projector, and the input lag from the television or projector is leading the image to be out of sync and the eyes are the wrong way round. And this allows those people to swap the projection from the game so that the eyes will then line up. The only alternative to this is wearing the glasses upside down, which is rather uncomfortable. If I press the button again, now this is now changed into side-by-side mode. Now if you're watching this on YouTube, you will now actually be seeing 4 images side by side. That's 2 groups of side-by-side images. That's just an artifact of how 3D Vision and Shadow Play works. Just kind of ignore one half of the image, just look at the remaining half and you'll see that we've got 2 images side by side. If I press it again, it's the same thing, but it reverses that. If I press it again, it's over under. If I press it again, it's over under, but now reversed. If I press it again, this is an old version of the shader that doesn't have the line interlacing. But anyway, there's also some line interlaced output modes in newer versions of the shader, which are useful for using 3D Vision on 4K televisions, which often have a passive polarized filter on every row of pixels that alternates in the polarizing direction. And so by having the pixels go to the television that happen to line up with that filter, then the 3D is in sort of a passive mode, so the television doesn't even have to be aware that it's displaying 3D content. It just happens that the right pixels line up at the right parts of the polarizing filter to render in stereoscopic 3D. And that's pretty useful because a lot of modern televisions have started dropping their 3D features, even though they still have the polarizing filters. But in addition to that, we also often use that in conjunction with another custom shader. I can't really demonstrate it because the the input and output looks exactly the same, so there's nothing really to see. It's an upscaling shader. It allows us to have the game render at a lower resolution and then upscale it to 4K and then run it through the line interlacing shader to use the correct output mode. That's pretty required because, as I'm sure you're aware, 4K is a lot more demanding on graphics hardware than, say, 1080p is, and 3D Vision is also a lot more demanding on graphics hardware than 2D is. In a 3D setup, we are rendering twice the amount of geometry and twice the amount of pixels, so as a rule of thumb, that'll lead to approximately half the frame rate. If we scale that up to 4K again, that's going to lose more frame rate. So trying to natively render a game at 4K in 3D with effects turned up is a pretty big no-no unless you have extremely good graphics hardware, and even then it's pretty bad. Anyway, to show some more of the custom shaders that we use with 3DMigoto, I'm going to have to jump into a different game. That's the only custom shader I've got set up in this one, so I'll be back in a moment. So the next custom shader I'm going to show is one that we ship with all recent versions of 3DMigoto. This is a custom shader that implements a software mouse cursor. Before I actually show the shader itself, I'll show what the problem is that this shader solves. So this game I'm using is Dreamfall Chapters. This is right at the introduction of the game, and there's something over in the distance that I'm supposed to click on, so I'll go ahead and click on that. Now the game has just revealed the hardware mouse cursor, and it's expecting me to click on one of these two icons that has just shown up. The problem is that the hardware mouse cursor is always rendered on the 2D screen plane. It is impossible to move that to depth. However, the icons that I'm supposed to click on are not being rendered at the 2D screen plane. They are being rendered somewhere much further off in the distance. So this doesn't really work. And the way we solve that is, of course, using a software mouse cursor, which we can adjust the depth of. So if I just reload the configuration with that custom shader enabled and now click on that again, now this time the game has attempted to show the hardware cursor. 3DMigoto has noticed that, and instead of showing the hardware cursor, it is now showing the software cursor. 3DMigoto has automatically converted the icon that's set in the Windows API for the mouse cursor into a DirectX texture. The shader that we've injected has picked up that texture and is now rendering the mouse where it would be, where the hardware cursor would have been, but now pushed into depth. And this means that I can now actually successfully click on these icons. This is also actually required if we're using any of the custom output modes that I showed in the previous video, which I think I have enabled here as well. So yep, in this case I do. Firstly, I'll go back and I'll do over-under. It might be a little easier to see on the YouTube video. And firstly, I'm going to go back and go back to the hardware cursor, which also resets the display mode. And so at the moment I have the hardware cursor, and if I try to click on any of these icons, I'll be rather unsuccessful because I have one cursor that can go over both sides of this and click on icons, but it's not completely not lined up. So if I now go back to using the software cursor shader and once again switch to over-under output mode and now attempt it, I can successfully click on these icons. So this is pretty much required custom shader as well, and hopefully that should be fairly self-explanatory. And I guess I'll move on to the next custom shader now. But I might show the game that where the custom shader feature originated from. So this is Batman Arkham Knight. Now this fix hasn't actually been released, and firstly let me just show you quickly what the game looked like before we got to it. So if I have a look at the city below me, if you're looking at this on a stereo 3D monitor, you'll see that all the lights are completely at the wrong place. It just looks like complete garbage. You can't really make out a thing. Now this game uses an effect called tile lighting. This was the first game where we came across this effect. It has since gained a lot of popularity, and many AAA titles are now using the same effect. However, we've never actually seen two games implement tile lighting in exactly the same way. It's always different every time we see it. Anyway, our first attempt to fix this game with the typical stereo corrections for lighting resulted like this. This has corrected the position of each of the lights, but as you can see there is now a very visible tiling effect caused by the tile lighting. However, this game presented quite a bit of a challenge, tracking down how to fix the tiles, but at some point we managed to fix them using a stereo correction just in a different point, which, look, game, just give it a moment, takes a which looks a little bit like this. Now the problem is that although most of the lights are looking pretty good, you can see that there is still some strange clipping happening on the lights on a 4x2 grid, much larger than the small tiles that we just saw a moment ago. Now this is an artifact because this game is doing tile lighting in 2 stages. It's using those small tiles that we already saw, and that's being computed on the GPU where we can correct it easily once we identify the correct location to do so. However, these larger tiles are actually being computed on the CPU, and 3DMigoto has no access to anything the game does on the CPU. 3DMigoto sits between the game and DirectX. It's in the rendering pipeline. It can't scan the game's memory, it can't modify the game's memory, it has no idea what's happening inside the game. All it can see is what the game renders, and since the game passed it a list of tiles that was already broken in Stereo 3D, we didn't have an opportunity to correct that in a shader as we normally would. And so this is where the custom shader support originated from, because the custom shader support was necessary to run an algorithm on the tiles that the game had passed from the CPU to adjacent tiles. And I've just reloaded and this is now completely fixed. As I said, this fix hasn't actually been released, so there are still some broken effects like that helicopter searchlight. But this is where custom shaders originated from. Now, before we ended up with this solution, we did actually try an alternative version where we did attempt to correct the buffers inside the tile lighting shader. However, this resulted in the frame rate dropping to under 10 frames a second, meaning the game was completely unplayable. And to understand why that is, you need to have a pretty good understanding of how GPU hardware and caching effects work. That's far too complicated for this video, so I'm not going to go into that. But the summary is that doing this in a custom shader means that we can do it with 0 frame hit. Tile lighting itself already costs quite a few frames a second, but this doesn't cost anything on top of that. At least not anything measurable anyway. So this is where the custom shader support originated from, and this is for running an extra shader on the GPU that the game didn't provide. This was nothing that we could patch. We had to write our own custom shader to do this support. That's where custom shaders came from. So in this game I'm going to show 2 of the more recent custom shaders that we've added to our arsenal. The first is a custom help text shader that renders some help text for the user to see, and we might use this, for example, to remind the user of any keyboard shortcuts that we've added to the game or other usage instructions. And the keyboard shortcuts actually kind of brings me on to the next point, because in 3D Vision there are 2 settings that control the stereo projection. I've just turned on the 3DMigoto hunting overlay so I can actually see what's being used in this game at the moment. This hunting overlay is not something that we make available to users. This is purely for people who are developing fixes to use. So the 2 settings are separation and convergence. Separation defines the overall strength of the 3D effect, and convergence, to try to describe it simply, convergence describes the amount of pop-out that we're going to get. And why this is important is because if the convergence value is too low, then the entire scene is too far away and it looks flat and it looks too large. And it's a pretty unsatisfying 3D effect. Conversely though, if we increase the convergence, which I'm going to do now, then at first we actually get a better 3D effect. At the moment I'm seeing a lot more depth, a lot more difference in depth between, say, this foliage at the front of the screen and the tree in the background. But if this convergence value is increased even higher, then things become quite uncomfortable. At the moment I have a leaf blocking half my view, and I can't really see much of anything. And if I were to keep increasing this, at about this point I can't really make out anything at all. I am effectively blind. So it is important that we choose a good convergence value for the game, but the problem is that a good convergence value is a little bit hard to define. For one thing, it can change from one moment to the next in a game. For example, a game may have a regular gameplay and a cutscene, and the cutscene may require a vastly different convergence value to be comfortable to view. In some games we may be able to pick a single convergence value, in other games we can't, and we have used various strategies to try to resolve this issue. One such strategy, as I mentioned earlier, was using key bindings to switch between a few useful convergence values, And we have other strategies like attempting to detect whether the game is currently rendering a cutscene or not, and we might do that, for instance, by detecting that the game is using a particular post-processing effect, such as depth of field, which is only active during a cutscene. But in some games such as this one, even that approach falls short, as within a cutscene we need vastly different convergence values from one camera angle to another, and there is no way for us to detect that based on the camera angle alone. So this automatic convergence shader is actually running on the GPU, and it's basically analysing the scene as a whole, and it's just looking to try to find the closest point to the camera on the scene. So in this scene, for instance, it would probably find some of this foliage in the foreground, or a leaf, or something like that. In other scenes it will find other things, and it doesn't really know what it's looking at. Again, it's not intelligent. In some ways it's actually fairly close to the automatic Crosshair shader. All it's looking at is the current depth values that the game is using, and using them to get a ballpark estimate of what a good convergence value might be for the current camera angle. Now if I leave this disabled and load up a cutscene at the start of this episode, then straight away in this cutscene we have a problem, because it's displaying a doll's head, I think. However, it's far too close and I can't focus on it. I'd have to go cross-eyed and it would be very uncomfortable to view. As the camera angle has panned out, this now becomes a lot more comfortable to view. However, the automatic convergence custom shader that we've implemented, which I'll now enable, solves this by, as you can see, lowering the convergence when something is very close to the camera. It's lowered it to 0.21 convergence, and as the camera angle pans out, then the custom shader is automatically adjusting the convergence value. So the next use of custom shaders I'm going to discuss is throughout the cutscene, inverting matrices. Now, inverting matrices is something that we need to do fairly often. The reason that we need to do it is because we are implementing stereo corrections, and the NVIDIA white paper gives us the formula to do that. However, that formula is specified in clip space coordinates, and if we need to inject a stereo correction in a different coordinate system, then we need to convert that into the whichever coordinate system is in use, usually view space or world space coordinates. And in order to do that, we need access to the, for world space, we would need access to the inverse view projection matrix. And in some games, that is already provided into all the shaders, and we can use it directly. However, in many games it is not, and we need to take the forwards view projection matrix and inverse it. And in some games make it even more difficult. Unity games, for instance, didn't used to provide this matrix anywhere that we could find at all, and we had to derive it mathematically from other sources. Now, Unity games have got a lot better in that regards, and now a lot less of the fixes of Unity games rely on that. We actually still have the code to do that in place. However, in most of the effects in this game are actually falling back to other strategies to render correctly in stereoscopic 3D, but there are a few effects here that are still using that strategy. The water in front of me is using that strategy for the reflection. There's also some windows behind me that are using it for the parallax effect, to give the illusion that there is a room behind them, and there are several other effects in the scene also using it, but it is pretty subtle. Anyway, if you are watching this on a 3D monitor, you'll be able to see it. If you're not, it'll move very slightly, but you won't be able to see what's actually happening. So I'm just disabling the custom shader and reloading, and the reflection that's in front of me is now flat. It is being rendered on the surface of the water, and the water looks very fake. It doesn't look realistic at all. That is not how water looks in real life. In addition, the parallax effect on this window has disappeared. As I move the camera, you can still see a parallax effect, but there is no longer a parallax effect between my eyes, so it appears that the room behind it is just wallpaper on the window itself. However, if I turn the custom shader back on, then that effect moves slightly into depth. It is very subtle, but it is enough to be fairly convincing that there is a room behind that, and likewise the reflection on the water has now moved back into depth where it belongs. So the next custom shader I'm using is actually being used to correct the light shafts in this room. So this game is using volumetric ray march light shafts. Light shafts are fairly common, but this particular variation on them is fairly rare. The frame rate in this room is absolutely abysmal because the game has chosen to use these, and these are real performance killers. But in order to render them correctly in stereoscopic 3D, we need to do some fairly advanced maths and coordinate transformations. That goes beyond what we would do with most effects, and in this case it's much easier to do that using a custom shader to patch some of the coordinates inside buffers, rather than trying to patch the original shaders themselves. Without this custom shader, the light shafts look like this, and if you're actually viewing this on a 3D screen, you'll see that this room is now actually rather difficult to view. It's got strange artifacts all over the room that make it kind of hard to see what's going on. They're rather distracting, and that's simply because the light shafts are being rendered in flat 2D at the screen depth. Even if you're not viewing this on a 3D screen, you should be able to see that those light shafts are no longer lined up with the window. Same up there, they're not lined up with the vent, and so on. So the custom shader, if I just go and re-enable it, allows us to correct these sort of fairly advanced effects that are difficult to do just by injecting stereo corrections as we would normally do. So this is Subnautica. This is another game where we've added the automatic crosshair so that the crosshair will line up with objects in the game, making it possible to interact with them. But there is a bit of an extra problem in this particular game, and that is that a little bit through the game you get access to this submarine that I'm currently in the cockpit of, and in order to operate the submarine, it is expected that you click on various icons in the HUD, and in 2D you would do so by lining up the crosshair with the icons and clicking, and it would be very simple. However, in 3D, the crosshair, as you can see, is not lining up with the icons, and if I attempt to click on them, even though it looks to me like I've lined up the crosshair with the icon, it is not registering. So we need to correct this, and the way we do it is by using 3DMigoto's custom shader feature. And I'll just reload with that enabled, and now you can see that the crosshair is lined up with these icons, and I can very accurately click on them. So I'm going to show another two custom shaders we use in this game. This is Watchdogs 2 from Ubisoft. Now this game is actually an EAC protected game, but Ubisoft provides a command line switch to disable EAC, which is what I'm using at the moment. Now, as you can see, the HUD is currently flickering. This is actually a game bug from Ubisoft. There is essentially a threading issue, as best I can tell, where the last couple of draw calls are performed in one thread, and then the present call is performed in a different thread, and they've violated the threading constraints of the DirectX API. When you do something with the immediate context, you're supposed to use a single thread for that. They have used two different threads, as best I can tell. And that results in the last couple of draw calls not always completing by the time the present call has gone through. And the way we fix this is by using a custom shader, which I will now activate. And it is, as you can see, the HUD has stopped flickering. And this is now performing a blit from the HUD's render target onto the back buffer, from the same thread that is being used to present the back buffer. So this actually corrects the game bug, essentially. Now there is a second bug. This one's a little bit more subtle. I'm not sure how well it'll show up on the recording. It's very precise. When the camera is in very specific points, the graphics in the game glitch out. You can see the shadow under the tree as I move the camera past a specific point changes the wrong color. In fact, the tree as a whole changes to the wrong color just as the camera moves through that specific point. And these points happen all over this game. Best as I can tell, it's some kind of boundary between two light volumes, and when the camera passes between that, the game is expecting that the volume will be either on one side or the other of the camera. However, because the NVIDIA 3D Vision driver has moved things to a different location to render in stereoscopic 3D, that is no longer the case, and that volume can be on one side of the camera in one eye and the other side of the camera in the other eye, and that leads to this glitch. And to fix this one, I have another custom shader which I'll now activate, and that essentially just corrects the rendering of that to remove the assumption that that volume is going to be on one side or the other of the camera. And now, as you can see, that's rendering correctly no matter where the camera is positioned. So the next use I want to cover of custom shaders is actually not something that we would ship to a user, but this is something that we would use it for to help us develop a fix for particularly difficult effects. And I just kind of want to include this for a bit of completeness to show what the custom shader feature is actually capable of doing. So this particular custom shader is used to help us fix the volumetric fog in this game. In particular, there are some sort of light shafts that are being cast, so the sun's up there and it's shining through the trees, and that's actually casting a shadow in front of me, and because there's some fog in the game I can actually see the shadow, and if I move around you can see those rays in front of me, and that is a fully 3D effect. Those are 3D light shafts correctly positioned in stereoscopic space, but they're pretty subtle effect and very difficult to see. On the video you can probably just see a slight hint of them. And so to help us get better visibility on certain difficult effects like this, sometimes we need to use a debug shader to help us do that. And I've just turned on the debug shader that I used for this particular effect. So this is showing me the shadow volume, and it's showing, this is actually not just a three-dimensional volume, this is a stereoscopic three-dimensional volume. So there are separate three-dimensional volumes for each eye that are rendering part of the shadow volume between me and the sun, and as I move around you can see that moving, and if you were to put on stereo 3D glasses and view this on a 3D screen, you would also see that these are not exactly the same between both eyes. There is actually some depth difference between them, and that was important to render this effect correctly. But like I said, that is not something, oops, I pressed the wrong button. That is not something that we'd actually ship to an end user, that's just to assist us in creating an effect. There is, however, another custom shader in use on this water that we do ship to a user, and this is another one that you can't really see. It's a very subtle one, it's a downscaling shader. So the problem here is that this particular water rendered back to front. The image for the left eye was rendered in the right eye, the image for the right eye was rendered in the left eye. And so to correct this I've actually swapped those around. I've taken the images and I've swapped them around. And on a single GPU system that's fine. But on an SLI system that creates a lot of work, because each card in an SLI setup is rendering the images for one eye, and when they suddenly need to swap images to the other eye, the cards need to talk to each other. And that takes up a lot of bandwidth. And the higher the resolution is, the more bandwidth that consumes. Now up to about 1080p in SLI, the performance of this is okay. But if anyone is using a display that is above 1080p, such as if they're using 3D Vision Surround, or if they're using a 4K monitor, or even something that's not quite 4K but still above 1080, the frame rate on this drops to unplayable levels. So in order to be able to do this eye swapping while still maintaining a playable frame rate, we first need to downscale it on each GPU separately before those buffers are swapped between eyes. And since the game does not provide a downscaling shader that we can use, the custom shader support is used to add this. Anyway, I think that's probably a pretty good overview of everything that we've sort of used custom shaders for so far and what the feature is actually capable of. Hopefully this shows that the custom shader feature is here for essentially two reasons. One is to add extra 3DMigoto specific features, 3D Vision specific features, such as the help text overlay, such as the 3D Vision to side-by-side, over-under and line interlaced output modes, such as the software mouse shader, and potentially other overlays that we may want. And in addition, we also sometimes use it for particularly difficult effects. But like I said at the start of this video, this is not how we fix most effects in the game. The custom shader support is only reserved for very difficult effects where we can't simply inject a stereo correction and have them work in stereoscopic 3D. But in terms of the question as to whether the custom shader support could give someone a competitive advantage in a multiplayer game, I really can't see how. No matter how much I stretch my imagination and try to imagine how someone might use this support to give them an advantage, I really can't come up with anything. Anything I might think of is really clutching at straws and not very practical. So I don't think that this feature is really a concern at all for multiplayer gaming.